Hello. Today I'm going to demonstrate a pulse to square wave converter. Many times in real life we have the case of pulse which we want to convert to square wave. For example, if you have a rotating disc with a light source and a center on the other side, and when the disc rotates, we will got the pulse from the sensor. Usually, this pulse can be processed for your ultimate purpose. But what if you want to have a square wave from this pulse? Now, the design of the circuit is catering for frequency of 1 Hz to 100 kHz, and for a duty cycle of 5% to 95%. So whenever there is a pulse within these two range, the purpose of the circuit is to get a square wave output with the same frequency and 50 duty cycle. Okay, this is the demonstration setup. I have already powered on the oscilloscope, and on its channel 1 we have a T connector. One end of the T connector has a coaxial cable, this one, which I will now connect to the LiGo signal generator. Now we can power on the signal generator and test the function of the circuit. This signal generator has a pulse function which allows us to change the duty cycle of the output pulse. So we select the pulse function. Right now the frequency is 1 kHz, the amplitude is 5 volt, and the offset is 0 volt. Duty cycle 50%. So effectively the output is a square wave. So we turn on the output and we get a square wave on the oscilloscope. The other end of this T connector has a coaxial cable going down to some circuitry. This is the coaxial cable. This one. And this oscilloscope is getting signal from the output of the circuitry back to the channel 2 of the oscilloscope. Right now the circuit has not been powered on, so there is no signal. Now I'm going to power on the circuit. Now you see two square wave. If we change the duty cycle of the input waveform, this is the input waveform, okay, to 40. Watch the blue trace, which is the output, does not change. It remains a square wave. We'll get it bigger. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 division. So you can see that the blue output waveform actually span 5 division. So these have a 50% duty cycle. Now we gradually reduce the source duty cycle from 40 to 30, 20, 10, oh, too much, 10, 5%. So this is 5%, 50%, 60, 70, 80, 90, 95. So this stat proves that at 1 kilohertz we can vary the duty cycle from 5% to 95%. Actually, the circuit can do more. Let's say 99%. Okay, still good. 1%. Okay, so let's pay it back to 50%. Now we change the frequency from 1 kilohertz to 1 hertz. Okay. I move see if the tray still have a nicer display. Now the duty cycle is 50%. Let's say 1%. So far so good. 99%. Okay. Still getting a square wave. So we have tested the 1 kilohertz, 1 hertz, and now we're going to test 100 kilohertz. Yes, we change the duty cycle back to 50%. Move the trigger point to back. Frequency 100 kilohertz. Okay. So right now the input frequency is 100 kilohertz. We then change the duty cycle from 50, 40, 30, 20, 10, 5, 60, 70, 80, 90, 95. Okay. So the circuit perform this power to square wave conversion from any duty cycle from 5% to 95%. So let's put the frequency back to 1 kilohertz, and then we can look at the duty cycle, 95%, 50%. Let's look at the rising edge. 10 microseconds per division, 5 microseconds per division, 1 microsecond per division. (500 nanoseconds per division), 200 nanoseconds per division, 100 nanoseconds per division. This is the rising edge of the output. Now then, let's look at the falling edge. Trigger menu. Triggering on the falling edge. 100 microseconds, 50 microseconds, 20 microseconds, 10, 5, 1 microsecond. Now we can see some small jittering at the falling edge at 1 microsecond per division. If we increase the speed of the scan, now we have 200 nanoseconds per division. You will see we have some jittering on the edge. This is a very vital clue to tell you what kind of circuitry is actually doing the pulse to square wave conversion. But when we slow down the scan speed to 2 microseconds per division, then the jittering becomes very small. I can say it's acceptable. So this concludes the demonstration of the power to square converter circuit.